Starting it here already. Thank you all for coming in person, and thanks for the people on Zoom. I don't know how many we have or if we have any people on Zoom, but probably we do. We have Professor Ankur Mehta today. Ankur is a good friend of mine, although I just met him a few months ago. I really like him. I hope you like him too, because he's super cool. So he wants to make robots accessible for everyone, which is, I think, a great mission. I really admire. He is from UCLA. He's a professor there. His lab is named Lemur, which is, I think, also very creative. He had his degree from Berkeley, and he has an MIT stuff before the UCLA. And now he's visiting us. He had a bunch of awards. If you're curious, you can go read the bio, but I think we should just listen to what he's presenting us today. So.
Great. Thanks, Anna. Thank you all for being here. For those of you on Zoom, I can't see you or your chats or anything, so feel free to speak up. And I'll say for everyone here as well, feel free to speak up. I like these talks to be a little bit more interactive. I'm happy to take questions from here. I can stand and talk on my own anytime, anywhere. You all are here, so this is really for you all to interact with me, and hopefully together we'll come up with some new ideas and new thoughts and hopefully make a change for the better. And so that'll sort of inspire a lot of this talk today. I'm trying to make a change, and so this may be a little bit of a different style of talk than you may be used to. There'll be some technology, some technical content and interesting videos and stuff. That's the second half of this talk. The first half of this talk is what I really care about. It's the motivation. And so there'll be a lot of maybe some social science that I'm going to throw into here. Before I get into that, I'll just sort of say that what I'm trying to do here is present the vision, the overall vision for my research lab. And as Zainab mentioned, my lab, the Laboratory for Embedded Machines and Ubiquitous Robots, it was there because I like primates, and lemurs are one of the few non-monkey primates. But in any case, we have a vision, and the vision is to get robotics everywhere. We really want everyone to have access to physical intelligence the same way as many people these days have access to computational intelligence. And this takes a lot of forms. It takes, it involves materials and manufacturing of the physical embodiments. It takes controls and algorithms. It takes human interactions and the mapping from designer intent to creativity. And ultimately, we want to put all this to get that final vision where everybody everywhere has access to robotics. Now that's a lot to go through, and so in this talk, I'll focus mostly on that, on the part that maps designer capabilities or designer intent to engineering capabilities. All the rest of the stuff, there's plenty more, and if you're interested, you can go to our lab website, and there's sort of research pages and research blogs and a lot more information about all the other work. And when I say all the other work, it's really the work that's done by my students. I just put a pretty face on all of this and come here and take all of their credit. So I'll be clear, everything that's in this talk is the work of my graduates and my undergrads that have been putting this together. Also, this is a good time to thank all of the sponsors and ultimately taxpayers like you who send the money to government, who brings it back to us that we can work on all this stuff. But so really, going back to this vision of our group, Lemur is there to try to democratize access, to get more people involved in the robotics story, to get people involved in the engineering process from start to end. And this is where I'm going to start the first half of my talk, which is the motivation. Why is this so important? Why is this the driving feature that has sort of influenced my academic career? And like I mentioned, this is going to be a lot of social science, and I'll say I'm not a social scientist. I am an engineer by training and by trade, and so I'll present a lot of these things as an outsider looking in. And so this is going to be my interpretation of the data and of the information that comes through the social sciences field. There's probably many other very reasonable, very rational explanations for it. And my take is just one opinion. I'm happy to hear other opinions, and if you have some more discussion that you'd like, please feel free to raise your hand and talk about it. But so this is going to be my view, and this is coming from the perspective of an engineer who looks at this and says, what can I do about this? What abilities do I have? And so I'll start by saying, this stems from this issue. There's this core issue of the gap, the divide between the haves and the have-nots of society, and this divide is growing. We can look at it as sort of a time rate where we talk about income, and the income of the highest earners is far more than the income of the median or lowest earners. We can sort of integrate that, take that over time, and talk about accumulated wealth. And we still have the same problem, that the haves, those that have wealth, those that have income, have a greater portion of the pie than ever before. And that's one thing, but if you look at those that don't have, the bottom half of our society has even less than it's ever had before. And now I'll say these numbers are specific to the United States. If you start looking at the world, this gets very dire. And there's always been some amount of inequality, and this is it's growing, but this is not just numbers. It's not just abstract concepts of money and wealth and income. This has a real effect. And so this we can say that the access to wealth, the access to resources, is very directly correlated to access to technology. Technology involves both hardware in terms of smartphones and laptops and other electronics, and services as well. The underlying support for all of this. Perhaps when I was a young lad, you could have a computer without an internet and it would still be useful. But right now, everything is driven by some amount of networking. And again, that is gated by access to resources, by income and wealth. And this gets us to the core problem, which is that technology leads to education. And there's a lot of data that's up here on the screens right now, and I want to sort of focus on the correlation between the two graphs, in addition to sort of the data within there, which shows the past 3 years of COVID-related issues, lockdowns, pandemic related shutdowns, and so on, has been a somewhat unfortunate but very revealing treasure trove of data that really highlights how important technology and access to technology is in terms of educational outcomes. And by comparing these graphs, you can see that with less access to technology in terms of internet-capable devices and internet itself, we have lower educational outcomes, lower learning. And of course, this does affect everyone who, the pandemic shutdown affected everyone. But those that had lower access to education had lower results coming out of it. And this is exacerbated by the original problem, which is access to resources, which is income and wealth. And this becomes a generational issue, where those who suffer some impact from due to other external limitations or effects on education are less able to bounce back the lower wealth, resources, income they have. Those that have not continue to have less. Another way of slicing this is through the pipeline, where higher income communities generate higher educational outcomes, and vice versa. And what this ends up being is a positive feedback loop. That as you have more income, you have more access to education, you build more knowledge, and you build more ability to generate more. But the flip side, where when you have less access to resources, less access to technology, less access to education, you spiral down. And positive feedback is sometimes desirable. What it means is that you're going to rail out, and we do not want to rail out as a society. We do not want the have-nots to have nothing at all. At least that's how I view this. And now, with this somewhat bleak picture, I would like to move towards a rosy outlook on this, but I'll make it one step worse. And that's this idea where it's not just about access. It's not just about access to educational tools and technology and education as a whole, but it's about engagement with that access. Even when you do have engagement, these lower income communities and lower resource communities make less use of it. There's lower engagement. And there's many reasons for this. Again, I'm not a social scientist, and I'm not purporting to know all of the answers, but there's a cause-effect relationship. Now, this data was gathered in the state of California, where I am right now, but it's sort of, you can extrapolate this to broader societies where lower income communities have lower attendance at schools. which means lower educational outcomes. And of course, this continues on that cycle where lower participation in the educational process results in lower further income. And one thing where this becomes a really big challenge is that it starts early. It starts as early as kindergarten, where you can imagine some of the most formative moments of participating in the educational process. If you do not take part of that, then the entire rest of the process suffers as a result. And now, with all this doom and gloom, is where I come in and say there's hope. There is an opportunity to address this. And once again, I'll continue to give my caveat that this is not the only solution. This may not even be the best solution, but this is a solution, and a solution that I feel like I have agency over. And hopefully, you all can take a look at this and build your own solutions, perhaps in the same way. I'll refer to a psychological, or I guess a sociological effect called the endowment effect, which is ultimately the act of creation generates personal value. This idea of personalization, the idea of being involved, being engaged, starts with feeling like you matter. Putting your effort into creating something, in this case, into some part of the educational process. And so hopefully, by enabling more people to have access to technology, in particular by enabling more people to have access to their own created technology, we can break this cycle. We can go through and say, perhaps we can enable more people to make use of all of the educational advances that, as a society, we have developed over the past years, decades, and centuries, and ultimately break free of this loop and bring up all of society, not just the upper crust. Now, that's my motivation. That's where I come from here with the idea of democratizing access. But I will say, as engineers, we often tend to be driven either internally or externally by other motivations. And I'll say this approach isn't limited to just questions of democracy, of democratization and fairness, but there are real engineering values to this core motivation as well. And to illustrate and to sort of give some insight into this, I'll make use of this figure that one of my colleagues, Achyuta Kadambi at UCLA, created as sort of a broader view of societal questions in engineering. And it sort of stems from this fundamental idea engineering is all about trade-offs. If you improve some metric, whatever metric may be, there may be some cost to another metric. And here we can think of the horizontal axis being any kind of engineering capabilities, any kind of engineering outcomes, and the vertical axis being any kind of social or sociological outcomes. And we can see there's some sort of trade-off between there. And what I'm saying is that I would like to focus on the vertical axis, try to improve the state of engineering in that dimension. But as we do that, we push the Pareto front out. We increase the capabilities of engineering across all of this. And as a result, we should expect to see positive outcomes across any metric that we may care to evaluate. As an illustration, I'll turn to this document from the 70s, the philosophy of Unix. I'm an avid GNU Linux user, and I like this concept the first point here is try to, when you're trying to solve a problem, when you're trying to generate an engineering solution to some problem, solve that one problem and solve it well. And this is something that, as we start transitioning to the technology portion of this talk, as a roboticist, we see the opposite of this very often. And here's some clips from the DARPA Robotics Challenge from a few years ago, where the core objective of this challenge was not to do one thing and do it well, but to do many things. And what ended up happening was many things didn't get done well at all. Now, of course, there was certainly a lot of success in this challenge, but there were also a lot of these setbacks. And the reason why this matters, I'll again return to that philosophy of Unix, it's this idea that part of development, part of engineering, part of generating successful outcomes is failure. Try, and if it doesn't work, scrap it and try again. Try something new. When you have a single monolithic solution like those Atlas robots or the big robots for the DARPA Robotics Challenge, each one individually has a huge amount of cost associated with trying. And when it fails, there's a huge cost associated with failure. this idea of scrapping everything and starting again inhibits progress in engineering. And so if we try to focus on reducing costs for development, reducing costs, and reducing the barriers to participating in the engineering process, not only do we reduce barriers, have more people participate in the conversation, but we can also iterate more. We can try more things. We get more people trying more things. We'll eventually get more solutions and move towards improving the technical outcomes of our engineering. And so this gives rise to the core vision of the central objective of a lot of the work that we do in our research. And that's this idea of using our abilities, using our engineering expertise, and using our research resources to give the ability to create to everyone else. The ability to design and manufacture and test and fail and iterate, ultimately pulling all this together to make robotics cheaper, more accessible, more democratic, and ultimately more performant, with better outcomes. So with that, I'll move into some of the technology that we've developed in our lab. Are there any questions though? This may be a good time to pause and talk about the motivation and and sort of the objectives behind where this is coming from. Yeah.
Have you done any like social experiments by using your like the low-cost robot? Let's say send them to kindergarten. Yeah.
Right. So that's a great question. It's sort of, it's great to have all this talk, and then we go off and go in the lab and do research forever. It doesn't really match. And what we'd like to do is say, how does this really translate to some of these social concerns? And I'll say that we've done a lot of sort of cursory experimentation. And there's been a lot of, that has resulted in knowing a lot of technological challenges that we're still missing. So we've taken our cheap robots and brought them up into a middle school classroom and had people play around with them. And we realized that as a result of that, it was a great tool to maintain engagement. I think one of the comments that we got at the end of that by one of the teachers was, this was the first time all year that we've gotten our students to pay attention to the same activity for an hour straight. Great, a huge amount of engagement. We weren't quite sure if they came away from that with any advanced learning. Did they get anything out of that experience? We realized there was a lot more that we had to do to enable that kind of learning, which led to some more research on that field. We very recently had a workshop where we brought in members of the public to go ahead and try this. And once again, very compelling. A lot of people found it very, very interesting. We learned that there's some more stuff that we need to work at before it becomes, before we can build that bigger picture. But so that's why this is, there's a research direction that we're going on. I'll talk about a lot of the results that we have, and I'll bring up some of the more work that we're working on to get to that vision where everyone can go ahead and use this. But throughout the whole process, we're sort of interleaving the science, the engineering, and the technology with these kinds of questions, making sure that we always have a few undergrads, high school students in our lab to play around with stuff, go out and talk to schools nearby and see where this can go, and talk to people who are not the standard engineers that show up in engineering labs. People from other departments in our university, or people who are not in the university at all. Yeah.
So particularly in under-resourced high schools and elementary schools and middle schools, there's been this sort of long history of ed tech stuff where we'll get you a smart board, we'll get you computers, and we'll do X and Y and Z, and they stick them all in the school. And I was at a school where they gave us 50 smart boards that we didn't have the resources to use, the teachers didn't know how to use. We grew up immediately, or they just sat in boxes. In New York City, there's a long history of this and many other places. So I guess maybe you can speak to, if the goal is sort of thinking about educational gaps as a measure of income, is the focus on this that we sit in the top, schools that are already well resourced enough to have curriculum development and other things to support it? Is it really to focus on sort of under-resourced school environments? And if so, then how do you address the sort of challenge where there may be many other problems that get in the way of being able to utilize technology in such under-resourced high schools?
Great. I think that last sentence that you just said really highlights my approach to this. There are many such problems that affect, the ability to participate in the educational process. Low cost or the cost of the technology or the cost of the educational resources is only one of them. And I alluded to a little bit more of that with sort of the truancy rates, where it doesn't matter how high tech your classroom is. If you don't go to class, you're not going to be able to make use of it. And I'll say there's definitely a few others that you sort of mentioned in your talk there, where it's not just the devices, but there's some supporting infrastructure that's necessary for the devices. I think these are all very important questions that I'll explain quickly now. We'll go through the talk, and then we should revisit this conversation at the end as well. I like to focus on all of those. So it's not just about making lower cost materials and making devices out of lower cost materials, but we want less infrastructure. You shouldn't need access to high-speed broadband or sophisticated computing or a classroom with some kind of network to do this. The idea is that we create these tools that anybody can have access to in their home, where you don't need the establishment of some kind of classroom to do so. You don't need any infrastructure. You don't need necessarily the rest of the educational process. Whenever you have the ability to participate, you should be able to get something out of it. And so low cost materials is one of the steps there. Infrastructure is going to be another big one. Just as a note, low cost materials, we think about paper, and then the infrastructure, we use scissors. So scissors and paper, maybe even tearing by hand. I don't know. In terms of access to networking and stuff, yes, there's that value that you could add by throwing some kind of network behind it. But there's stuff that you can do with it alone in isolation. And that's the general idea we want to go through, which is the more you can build around it, the more value it'll have. But it never drops to zero. Okay. Great. So I think that's a good time to jump into the work that we're doing here. And we're going to refer to this as printable. This printable means a lot of things to a lot of different people. Fundamentally, what we're talking about printable is manufacturable at home. And when I started my group at UCLA, this is what we had in terms of printable robotics. The quality of the video shows that this was 7 years ago. And it was this idea that we have a bunch of robots that we could make at home using low-cost materials. In this case, it was folded paper. And being folded paper, I'll also be using the term origami inspired. It's cut and fold manufacturing with paper. And what we did was we took this entire concept of a robot, which has this the structural embodiment, and we took that and made it printable. That is, we made it out of paper. You take a sheet of paper, you cut it up, you fold it up, and you can build that robot body. And we had robots that wheeled around and walked and manipulated the environment. We had other kinds of robots, and ultimately the structural body we took down into a very low cost, low infrastructure way of manufacturing. But that's not all a robot is. A robot has many other components, in particular, the things that give it intelligence, the sensors, the actuators, and the controllers, that in the past we would use discrete electronic components to put in there. And this provides some of those barriers, the barriers to access, because you need infrastructure to get access to those things. They may be low-cost controllers and low-cost electronics, but you need a supply chain. You need to know how to use these things. You need to know about electrical wiring and how to test and debug these things. And I'll say there's another part to this to the robot, which is the power source. In this case, a battery. We're not going to focus on the battery. That's a much harder question. We're doing some collaborations trying to get power onto these things. We're doing some newer work that doesn't use electrical power as battery. We're going to say there's going to be some power source that we can throw onto here, but ultimately we'll take all of the rest of the robot, the intelligence, the thing that makes it a robot, and wrap that up into the printable paradigm as well. And the way we're going to do that is by taking our body, which was made out of paper, basically any thin film material that you can pattern with 2D manufacturing techniques, a fancy way of saying scissors. And we're going to augment that with a new material that is, again, similarly accessible, in this case, nylon sewing thread. And to make our lives easier, we're going to talk about conductive sewing thread, so it's nylon sewing thread covered with silver paint. Again, it's still a very low-cost material. Because it's conductive sewing thread, it's a little bit less accessible. There are workarounds that we can play around with by putting conductive wire parallel to the thread. But ultimately, these two together will give us a pathway towards this idea of fully printable robots. All of this stuff, minus the power source, being able to be integrated into a low-cost, easily accessible manufacturing technique. But we need some careful engineering design to make this happen. And jumping ahead to the punchline, this is the first design that we came up with. It's made largely out of just random 2D materials, the 2D material, which is paper or thin film plastic or whatever, and this conductive sewing thread. And what it does is it takes a constant power supply in and generates oscillations. It takes that the middle active beam of the material and it flips it back and forth for very low cost. So the overall cost in terms of all the materials, in this case, is a few pennies. And you know the one downside, the trade-off of low cost device is that it takes some time to assemble, to build. Like after one or two practice tries, you can get down to like a little over an hour. But ultimately, this I feel is moving in that direction of accessible, of minimizing the barriers. And I'll show you how this works in action. We have a constant power is being sent in, and what ends up happening is as that power is sent in, there's a mechanical process, an electromechanical process that causes the middle element, the active structural element, formed out of paper to just oscillate back and forth. There we go. So the general principle behind it is that the conductive sewing thread, the nylon, is a thermoplastic material. When it's the paper body gives it a particular structure so that when the middle beam is flipped to one side, current flows through the actuator on that side. It's under tension, current flows, it heats up. This is where we don't necessarily need to be conductive as long as there's some way of flowing current, perhaps by a wire instead. Resistive heating will cause it to heat up. It'll generate a tension. It'll pull that active element towards the right, or in this case, yes, towards the right. Basically, it'll pull in on that until at some point the active element is a bistable beam. It's a buckled beam built out of paper, exploiting the properties of thin film. It'll snap through. It'll flip to the other side, and the string that was under tension is now no longer under tension. No longer maintains electrical contact. No longer is heating up. It's back to cooling down. However, the other side, the other contact, is now connected, generates its own current, conducts its own current, generates its own heat, starts applying its own force, and eventually also snaps through. You get this oscillation. It flips back and forth, and from a constant power supply. This is the rudimentary beginnings of some kind of printable intelligence, programmed behavior. And I'll say it's very simplistic behavior ahead, but it doesn't stop there. We can actually now turn this as the active element into a robot, into some actual system that we can now assemble. And in this case, I'll give one example which uses no more, which just sort of builds off of that structure. And in this case, we're again making more use of the material properties. We can think back to when I was talking about how increasing the accessibility by making this out of paper also generates some values in terms of performance. We're using the material properties, the flexible substrate, to build these linkages. To be able to say what we end up doing is connecting that mechanical oscillation directly to a driver, to something that generates motion. And you sort of within the same mechanical structure, single manufactured process, we can go through, and as the beam moves back and forth through the linkage, you end up with a flipper that flaps up and down, generating forward thrust. And here you can see the robot itself without any current. It stands still. As you feed in a constant current, the flipper starts oscillating. There it goes, and you get this thing moving. You now have a robot that was made for, again, a few dimes. I think the overall cost was 40 cents. It used, in this case, because we're putting on water rather than the paper that gets waterlogged, we used a polyester sheet, thin film paper, thin film plastic, and this conductive sewing thread. We can use this same idea for a different kind of robot. This is now a robot that crawls over land. we added a new, some additional material to it. Basically, we added some more weight to the to that bistable beam in the middle. And now every time the oscillator switches back and forth, it generates a little bit of an impulse. Again, using the properties of the material, we're able to generate asymmetric friction. And every time the oscillator flips back and forth, it generates a pair of asymmetric forces, one of which is canceled by the friction, the other one propels the robot forward. This oscillator, it's not just a mechanical oscillator. We showed two examples of using the mechanical oscillation as the power behind some robotic system, but it does open and close electrical contacts, and so we can use that electrical oscillator as a part of a larger scale electrical system, and we can say that these switches, as they go back and forth, we can connect them to whatever else we want to connect in the electrical domain. In this case, we're just going to use LEDs as an example, and using this, a single constant power supply will make some kind of animated display. And of course, it has some amount of programmability. In this case, by changing the current, you can change the rate of oscillation. There's sort of a lot more that you can play around with here, both in terms of mechanical design and the electrical design of this. And we can start thinking about assembling this up into higher order creations. And we can use this system as the base, not just of oscillations, but now is where we take that and translate it to larger scale intelligence. We can use this as the base of logic gates. In this case, we can make a multiplexer, and a multiplexer is a universal gate, which means through this we can cascade them to make a bunch of further logic. In this case, we can start with a very simple NOT gate. You can take any kind of sensor input and invert that and generate some output. We can generate any kind of other gates. We can cascade gates and make larger logical sequences. And I'll say that we've done so and wrap this up into robots that have much more capable intelligence, that have sensors that we can print, and we can use that and process that using Boolean logic, and then drive that in various ways through the outputs. And now this is all well and good if you want to make paper robots for really pretty videos to show to a bunch of students. But going back again, there are other engineering benefits to this. And one of the things that this becomes useful for is the idea of generating or designing robots that operate in harsh environments. These robots don't have any silicon at all. There's no discrete components. And so we can put this underwater, and this will work just fine. In fact, it works a little bit better because water is great at transmitting the heat away from the thermal actuators. We can put this inside a magnetic field, and you can think about robots that operate inside MRIs or other NMR-based machines. Again, without any silicon components, we now have a much broader range of environments, before which we didn't have robots that could really work well, but these paper and string-based robots can do just fine. And I'll say I had a few other conversations earlier today about not just magnetic fields, but other radiation fields. And think about how can you run these in environments where there's strong microwave radiation, or perhaps other kinds of fields, where again, without silicon, these things are not impacted. And I'll say this is sort of the basis for our most recent award from the DARPA YFA, which says not only is this able to operate in harsh environments, not only is this able to be designed and built on the fly by people in the field, but without any semiconductors in here, without any silicon-based electronics, we now have a little bit of inherent security, where we're not reliant on semiconductors coming from overseas. We're not reliant on the shipping lanes being open and supply chains. We're not reliant on validating a whole bunch of really inscrutable pieces of silicon to make sure it does what we need. All sorts of very interesting directions now that we will be taking this work and building on to make this idea of mechanical intelligence provide value, not just for lower cost robotics, which is what I care about, but for a whole range of enhanced performance for robotics as may be interesting to a wide variety of people. Now, I'll say with all of this, there's the question of building the robots, which I talked about, but there's also that question of design. I mentioned that they are being able to be designed by people on the fly. And I'll say up until now, this idea of printable robots, printable robotic design, has been driven by experts. And I'll say, I used to be the expert, now I'll defer to my students, they're the experts. They're the ones that have to put together designs, PhD students in engineering. And that's because that comes from a lot of the validation. We're trying to accomplish some sort of behavior. And these are complex mechanical systems. We need to validate their performance, and a typical way to do that might be to use some kind of numerical methods, finite element analysis. But of course, these tools are very difficult to use, very difficult to spin up on. And trying to get access to those plus use those requires that expertise. That's not the only way to do it. You could instead use some kind of kinematic low order mathematical models, which are a lot less computationally heavy, don't require any custom tools. You can write these in Python, but the results are not very good. And now you need the expertise again to go ahead and interpret what that means in terms of, is your robot going to do what you want it to do? Do you need to change your design in some way to accomplish your goals? And pulling this all together, we now have a new challenge, which is, sure, somebody can build these robots on their own at home with their available materials, but what are they going to build? How do we map the design intent, somebody who has something they want to build, to the actual performance that we're going to get out of the system? And we can use that previous robot or that previous mechanism as an example. We have this oscillator that we're trying to get to oscillate back and forth. And we can imagine that one behavioral property of this may be the period of oscillation. And this is an example where, I'll run through this, but this is sort of a broader view of how we can think about the design process. We want to go through and say, how do we characterize this design, which consists of a mechanically buckled bistable beam and a thermal actuator, the thermoplastic conductive actuator, together in this integrated system to make this performant measurement. And now, how do we go ahead and do this? This is where I wow you all with my brilliance and say there's a bunch of math involved that we can go through and talk about really complicated differential equations. We can put this through some physics and talk about how the behavior of the materials across the different domains comes together, throw in some engineering in terms of low order modeling and approximations and assumptions, integrate that all together. And in 3 slides, I cover about 2 PhDs worth of work and talk about, hey, we have results. We actually know how to characterize the system and map the design parameters, what you would need to do to build the system, and turn that into the behavioral parameters, what you want the system to do. So clearly, you can all take a look at this and see exactly how to design your next bistable oscillator. Except not really, because that's not anything that anybody is expected to know. The thing is, this becomes a tool, a framework that we can actually throw into a computational tool. This is not designed for human consumption. We, as the human engineers, as the experts, pulled it all together to wrap it up into something that's computationally tractable. So somebody can just go ahead and throw this into a computational optimizer, a numerical optimizer. We're not an optimization group. We didn't come up with any kind of optimization tools. Any off-the-shelf optimization will work on this. It's a constraint optimization problem that's been around for, the problem of generic constraint optimization has been around forever. And we can go ahead and throw this into perhaps FMinCon and MATLAB or Python. NumPy has its own variant of optimizer. And we can now use this as the design approach. So we can say, again, there's some behavioral objective that we'd like to meet, perhaps meet a specific period of oscillation for this oscillator. And we need to figure out the geometry, the design that we need to manufacture, all the lengths of the pieces that we cut out and fold up in our printable process. Because this is an optimization, we can set some optimization target. In this case, we may talk about robustness. We want this to be accessible. Maybe you have access to a high performance laser cutter that has very high precision manufacturing. Maybe you don't. Maybe you have scissors, and you're trying to sit here, draw this with a ruler, cut it out. You're going to have some error in manufacturing. We want this design to be robust to the error. And throw this through an optimizer, and you'll get an example. And this is in contrast to perhaps without using any design tool, you just play around with some designs and maybe you came up with some other set of geometries that got that same performance, the same nominal performance, but under variations, under the same variations in manufacturing, those tolerances, you get a much higher variation in output behavior. So this is sort of just as an example of how we can throw our engineering knowledge into the pipeline to be able to simplify design for future designers. And I'll say this doesn't necessarily need to be just a single forward pass on design. We can turn this into a enhancement pipeline where there may be an existing design that somehow doesn't work according to designer's intent. And I'll give a very specific example that came out of a separate research project that we did, where we're trying to build blimps, lighter than air vehicles, big helium balloons that fly around. They need to perch every once in a while, and so we wanted to get them and to get them to grab onto a railing and stop there. And when you do that, it turns out that you have a large amount of force, the force of wind blowing on balloon, concentrated at a very small place, the gripper, and we wanted to build these lightweight grippers. Again, another value add to the low cost manufacturing. It's also low weight manufacturing. Folded paper is very lightweight. It works on blimps, but it's not very strong. And you can see that under the wind conditions, the blimp fell off of the perch. Well, we can go ahead and use our computational or mathematical understanding of the system, our low order models, to throw this into a computational evaluation tool that will identify that the source of the problem is weakness in the structural material. And this weakness can be enhanced. We can strengthen it using corrugations. By folding paper back and forth, we can get a stronger, more rigid structure there. However, doing so adds more paper. The whole reason we were trying to build this out of paper in the first place was to make it lightweight enough to fly on this lighter than air vehicle that has single digits of grams of payload capacity. Well, ultimately, we can put it all together and figure out the right trade-off across strength and weight. And again, with this computational optimization tool, there we go, we can build a much stronger gripper that doesn't blow off with wind. And it's light enough that when we do let go when we do let go and fly around, it's light enough. It doesn't weigh down the overall system. So what we've done here is we're sort of taking our knowledge, taking our engineering knowledge, wrapping that up into into some computational development tool that enables other designers to do the design. Now, when we talk about this in here, there's still the designer. The human needs to be a part of this design loop. We don't want to remove that in particular. I don't want to remove it because that's the whole point. We want to get more designers. We want to get more people participating in the process. Now, when we do that, we want some way of evaluating. And so auxiliary things that come out of this are perhaps there we go. In this case, it's a middleware platform where we enable, in order for us to do the evaluation, we need to figure out how to map the models, the computational models, the numerical and analytic models to the real hardware that was developed. And we do this for testing our systems. It turns out it becomes very helpful for people to see how can we correlate the physical devices that we built from the design that we've intended to create. This becomes a way for the designers, the people in the loop, to rapidly iterate over designs. Do a bunch of designs in the computational system, go ahead and then realize that in the mechanical system. If it fails, identify where things have gone wrong and address it and fix it and change it in the sort of try early, try often, fail, and iterate process. Now, again, this is where it comes back to this idea of hidden benefits, of additional value. We can take this thing where initially we would talk about having a designer iterate through their designs and try iterating on the design until they found something good. We can put this into a learning loop and talk about residual learning and figure out why is it that our low order models or our computational models or even our physics-based models don't match reality. And we can come up with a new learning-based model to make better understanding of how these low-cost devices end up working out. And so, this becomes another platform that we can build on as we go forward. Thinking about how do we map our computational understanding of systems, of these low-cost electromechanical systems to the physical instantiations of them. This is all sort of designed for behavior, designed for functionality. We can also think about design for manufacturing. Not only do you need to create a system that behaves the way you want, but before it can behave, it needs to be built. And it needs to be made in a way that you can assemble this thing. And so this is an example of using our design pipeline or design process to think about what are barriers to manufacturability in terms of, in this case, we're talking about electrical circuits specifically, where maybe trying to solder a whole bunch of resistors on an LED board is more effort. It's time consuming, it requires dexterity. But if we can find a way of collecting a bunch of these into a multi-factor system, if we can find ways of repurposing different circuit elements into a broader view, we can make a simpler board to assemble. We can have fewer discrete components. We can have lower cost materials and perhaps more reliable electronics. Ultimately, as I'm trying to keep to the time, I'll say that this is sort of the approach that we take for many different projects within our group. And it's this idea of taking a problem, taking an engineering problem that needs solved, and figuring out what is that barrier to access? What is that resource that is currently limiting the successful solution to that problem? We'll go ahead and take that resource and figure out how to build a computational model of the mapping from that resource to the problem, and then turn that into a computational pipeline for human-in-the-loop design. We can do it for a variety of robotics problems. In this case, sort of some of the input side of robotic development. We can do similar for some of the output side of robotic development. And ultimately, throughout all of these projects, which I'm happy to talk more about any of these. Feel free to ask me questions about them. This is all projects that we've done where we start from this idea of improving access by lowering resource costs, throwing it through some computational design, computational fabrication pipeline, and ultimately ending up with that core vision, where we want to take our abilities, our resources as engineers and researchers to give the ability to do research, to give the ability to do engineering, to give the ability to create to everyone else in the world. So I appreciate you listening all here. Thank you for your attention. I'll say that this is a time for questions. I would love to hear from you. What were you inspired by? What did you take away from this? And how can we work together to go ahead and build the future that really benefits all of the future? Thank you.
10 minutes for questions.
Okay, I have two, and we'll see. We'll go through one and then we'll time. Right. So I think it's really cool because usually when you think about low-cost robotics, we think about using existing robotic design and lowering the cost of components. But you've gone totally reverse. You said, how can we start with low-cost components and then work up to robotic design? But then, of course, that begs the question of how far can we go with components on this scale of cost? And I guess into that, you mentioned that you would love to get sensors into this like 2D manufacturing thing too. Do you have plans for how we get sensors? Once you have sensors, we can start closing loops and we can start doing a lot more intelligent behaviors. So how can we kind of keep pushing this to get closer to the capabilities of robots that we think about?
Right, so that's a good question. I'll answer the second half first. In terms of sensors, I showed in here actuators, I showed controllers. I didn't show sensors. We have sensors. There's a number of sensors that are sort of easy to implement with this, touch sensors or sort of contact sensors, where you can think about that central bistable beam where we use a thermal actuator to flip it from one state to another. But we can use contact to flip it from one state to another. And there you go. Now you have a sensor that integrates completely within this paradigm. There's plenty other similar kinds of contact or motion-based sensors. This is a thermal actuator, so we can think about thermal sensors. There's a lot of sensors that we do have in here. I didn't have a chance to go through all of them there. But now the other question, and I think that you touched on sort of the key approach that I'm bringing here, and the vision that I have for this future, where we're not trying to say, here's a system, here's a behavior, here's a robot that we work. How do we replace elements of it with lower cost materials, lower cost lower resources, and then try to recreate that capability? What I'd like to do, and what we've done here, is say, here is the low cost systems, the low cost components that we're building up from. What can we do with this? And I view this as a very sort of important distinction, because in the one case we say, here is the functionality that we want. And because this is the functionality we want, there's a lower barrier. Below this amount of resources, you cannot participate in the story. And maybe we can bring this barrier down and bring it lower and lower. But ultimately, there's those who can do this and those who can't. And what I'm saying is, let's just start down here. Let's figure out what is it that people do have. And with that, what functionality can we add? And as you mentioned, right now, it's not the functionality that we may consider like robotics. Not that, the world of robotics has gone far beyond simply getting a boat to swim forward or having a car navigate a maze. But right now, with below some threshold, you can't do even that. And so that's what I want to focus on, which is say, let's focus there where we start with whatever people do have. And we'll build any kind of capability, because that kind of capability is new. That kind of capability is something that doesn't yet exist. We'll add that. That's adding value to the world. And in doing so, we will find something else to manipulate across there. And that's what I was talking about, sort of, manufacturable on demand, and secure mechanical intelligence, and so on. But really, I think that you've sort of highlighted that distinction. The question is, where does this end up? That's exactly what this research is all about. Where can we go? I haven't found the end to it yet. There's, every time we do something, we come up with something more. Hopefully, as all of you go away and think about this and maybe try to maybe use some of these technologies or just think about this in your own work, we'll discover that there doesn't need to be that limit, that lower bound on what you have, so that to address what you can do. So I really think that this is the exciting question going forward, is where will this end up? Sorry. Let's go here. Yeah.
So as like a lot of technology develop and things become cheaper, things become smaller, whether that's sensors, actuators, computers, electronics in general, what is these since your work is a lot about making more accessible and more expensive, what is one such development that excites you the most? Like what part of the robot becoming more accessible makes you the most effective? Batteries, is it computing?
I see. So, I guess the question is what about this excites me, and I'll say that the thing that I'm most looking forward to is less about any individual component. Yeah, every time we make a different kind of actuator, that's cool. We add some more bits to our library. Every time we add a new sensor, a new controller, maybe some new power system. What I really like, what I'm really driven by, is the integration. Right? What we're doing is we're coming up with a framework that anytime somebody comes up with something new, and it won't be me at going forward, it won't be my group, hopefully it'll be all of you. We still want to be able to wrap that into the bigger picture that is robotics engineering. And by coming up with those frameworks, by coming up with that language that allows for all of these things to play well together, I think that's going to be the real thing that drives innovation. Because as we're starting to integrate more of these things, somebody else from some other background will have some specific thing that they want, some specific thing that they can create. And what's limiting them is the ability to integrate that, to work that into the ecosystem and build the actual robotic solution for them. And so I think that's really where I'm most looking forward to is that sort of like unified approach to developing system solutions.
Did you consider sustainability in designing robots? Like, if you want to make the robotic materials recyclable or biodegradable, if you want to fabricate those low-cost, massive robots.
Right. So the question is on sort of the sustainability of the materials processing, and I'll say that our answer to that is sort of a part of a bigger approach to this, which is that we really don't want our system capabilities to be contingent on material availability. Again, this starts from the notion of accessibility. If we say that we need to use polyester sheets, well, not everyone has access to Amazon next day delivery to get polyester sheets. But if we say it's any arbitrary 2D manufactured material or 2D structural material, some people can use polyester sheets, other people can use newsprint, some people can use banana leaves, right? And some of these are more sustainable than others. And ultimately, we can say that as we go forward, if we introduce a constraint of sustainability, if we introduce a requirement that these things become biodegradable, that as you iterate and throw away a bunch of designs, you're not causing undue impact to the environment, well, great, that becomes another part of the optimization criteria, where ultimately perhaps that will restrict some of the designs that you're able to do, but you can sort of build the designs in that space.
Should we ask Zoom? Is there any Zoom questions?
Sure. Are there any questions on Zoom? I can't see raised hands, so maybe just unmute yourself and speak up. All right. If not, lots of hands. Go in the back corner there.
Speaking of adding constraints onto the computational design, it seems like a lot of the advances that have been added to like your framework and your library have been about the accessibility of materials and also the just like the materials being low cost themselves, accessibility to cost. Have you worked along the constraint of engagement, which is something that you talked about in the first half, which is like, have there been specific considerations into engagement in any of the things you had added to your library framework?
That's a great question. I did bring up the engagement earlier, and I didn't really talk about that here. Engagement is a very difficult a difficult thing to quantify, except in the case where you bring this to a classroom and everyone's participating, and the teacher's like, hey, that was awesome. And I think the way we view engagement is by trying to keep our approach very general, where I don't want to say that this tool is used to make wheeled robots run forward. And so, I'll like, as an example, I have this wheeled robot that drove forward, or the boat that swam. Somebody took this paradigm and turned it into a seal that had little flappers and kind of like waddled forward, because that was what was compelling to them. And I think that goes back to this endowment effect. If you give them the ability to create what's compelling to them, then they become more engaged. And I think that's where we approach this question of engagement is, we'll come up with this library-based model and a bunch of these tools, but we'll come up with a few examples that show what are the variety of things that can be done, and we let the people who are designing come up with their own design. And hopefully in that way we'll get that bump in engagement.
Thank you for your welcome. I was just wondering about your outlook on this process of evolving human in the loop and the challenges are there, especially if you were to kind of start building towards more complex behaviors and within the optimization framework, be involved more and more wrappers, there's sort of issues with human understandability and control within this framework overall. So I'm wondering if you could speak to that.
Right, and I think that's a great question in that, what I mentioned earlier was that we want to keep this as a human in the loop process, so that there's a human. And when there's a human in the loop, when there's interaction between some human and some computational design process, there's some communication that needs to happen. And I think that's an area where we've certainly started some work. There's a lot more work that can happen. I'll give some insights and thoughts that we've put into this, but I'll say this is all future research. This is all stuff that we're sort of working towards. You hit on a very important question, which is how do we ensure that we understand what the designer wants in order to put that into our system so that our computational engine can give them something. On the first, the first approach to that is we don't need to be that good. We'll try whatever we can, and then there's just iterations that happen. And that was sort of the middleware that I showed, where you try something, you're able to view it in simulation, you're able to show what it would look like. You're like, that's not what I wanted. Let me try it. And ultimately, as you iterate through that, you'll come to a better merger between what the creator wants and what the design tool gives you. I'll say we don't necessarily have a very good, a very specific model for that communication, and we can think about how we can perhaps use natural language to make that balance. And this becomes something that's particularly interesting because a lot of times creators or designers are limited in how they can choose, how they can express their design intent. And this is not a question of design intent specifically in terms of computational design, but in general. Even two people trying to talk to each other need to overcome some kind of mental model mismatch. And so perhaps there's something there where we can make use of the fiddliness, the impreciseness of natural language to be able to try to merge those ideas together. And perhaps there is some iterative learning that can happen. As you design more things, you'll see what kind of changes you needed to make to the design output, and throw that into some kind of optimization loop to better understand what the meaning of that communication is.
For 5 years, method of converting the string ocean to sort of like an animal, very nice. It does seem a little slow. Have you guys tried any multi-threaded approaches?
Nice. It's interesting that you say that, because actually the way you get more performance out of it is you twist together multiple threads. But I'll say that this is, that the speed of this behavior is one of the downsides of using thermal actuation. It's limited by thermal time constants. We're working on some other approaches, making use of the same concept, the same mechanical intelligence concept that are not driven by thermal actuation, but perhaps by others that are sort of still underworked, perhaps optical, perhaps other forms of mechanical deformation. Really comes down to having some kind of nonlinearity driven by some kind of deformation, of controlled deformation. There's a lot of places this can go. There's pneumatic work. There's some other flow-related work. There's a lot of stuff. So yeah, multi-threading is only one possible approach to speed up.
And then a quick follow-up. This work seems kind of a little extreme in terms of low cost. I've seen like other sort of low cost for $2, it's like on the cents. If you were to, let's say, add maybe $1 or $2 more, how would that, I guess, change your design process or the types of capabilities?
Right. I think that's a very interesting question because I came from the robots that were $10 robots, and I think I give $1 as sort of an arbitrary milepost. Really, the question is less about the material cost of it and more about what access you have. And so $1 is, it turns out $1 is actually quite a lot for in terms of disposable cost for most of the world. And so even $1 may not be the right target. If you had the ability to add cost, there's no end to where you might want to use it. You can say one of the challenges here, as I said, was speed. So rather than using this thermal actuator, let's just go ahead and use a pager motor. Pager motor costs about $1. And it's still an electrical thing that operates under the same amount of current, but it's a lot faster. But it's not just about that $1 or the extra dollar of cost there. Now you need to have some ability to buy a motor, and get that motor delivered to you, and have some way of being a part of this overall ecosystem. And so adding more resources, there's plenty of ways of using that. I'm concerned with removing more resources.
Okay. Ankur, thank you so much. It was very inspiring.